should be started. All right, so this is my project for EC551, which is a network on a chip. The general motivation here is that a lot of digital systems, their performance is limited by their communication. And I have a quote here that's, as technology improves, memories and processors become small, fast, and inexpensive. The speed of light, however, remains unchanged. So the idea here is that our logic units and our memory units get better and better, but we're still constrained by the propagation delay of our communication. And so how we manage that becomes really important to the performance of our systems. So the definition I give of the interconnection network is that it's a system that transports data between endpoints, which is a really generic definition, right? It fits a lot of different examples, which I give here. So there's an on-chip network, so delivering data between registers and other arithmetic and logic units. You can have system-level networks, which are for multiprocessors communicating to memory and with each other for, say, cache coherency or something. And then even local area, wide area networks like the internet that connect many systems across long lengths. So I'm particularly focused on a network on a chip, and this is a packet-switched on-chip interconnect. You have a set of routers that are connected to each other, and each one comes with a network endpoint, and these are connected point to point. So I'm explicitly not talking about these local area or wide area networks here. And the significant difference is that I have much shorter channels and much higher data rate. And so the solutions that I will go after in a network on a chip are going to differ from what you'll see in a large area network. Feel free if you have questions at any point, just ask. So I give a few examples of topologies of networks. So the first one at the top is sort of if you had to connect, so the black circles are endpoints. If you had to connect a number of endpoints, one of the first things you would do is just a multi-drop bus. So all these 4 endpoints are connected to the same bus, and they communicate on that. And that's probably typical of what you would see in the late 80s as far as an interconnect. But the problem is that as you add more endpoints, the performance doesn't scale because you're still limited by the one bus. And you need to arbitrate access to the bus. You can't have everyone communicating on it. And you might go to the other extreme, which I've drawn in the top right, which is a fully connected point-to-point network. And here, as I add more endpoints, my performance scales, but the problem is that the area and power of such a network doesn't scale as well because I have to have quadratically many connections between all the endpoints. So what's typical of a network on a chip is that I have some connections and I'm doing point-to-point communication. So I've drawn 2 very typical ones. This is a 2-dimensional mesh, so everything is connected along the x dimension and along the y dimension to their neighbor. And similarly, a torus. The only difference between the torus and the mesh is that the endpoints are wrapped. So the endpoint here in the bottom left is a neighbor of the one on the bottom right, and that extends also to, however, this is a 3x3 torus, and you could extend that larger. Typically, what's done are some sort of 2-dimensional structure, and that's because of just the way you fabricate a chip, that 2 dimensions happens to map pretty well to the fabrication that you'll see. I've, in particular, designed a router only suitable for a 2-dimensional mesh. There are 3 main parameters that go into your network. One is the topology, how many routers I have and how they're connected. I just talked about that in the previous slide, showing meshes and tori. The second is that the routing function, how I'm going to route through my network from the source to the destination. And I'll talk about that in a bit. And then the third, which is more or less the focus of the talk, is flow control, which is when can I forward a packet, or I talk about pieces of a packet called flits. when can I forward it to the next router? I need to make sure that if I'm not routing everything instantaneously, that I have space to store a packet if I don't have enough room to keep routing it. Then, I mean, this is sort of a short point, but there's a lot of meaning to it. So how you pick the topology or the routing function or the flow control affects a network's performance, cost, and efficiency. And when I talk about performance of a network, there's two primary metrics. One is the latency. So how long does it take me to send a packet from source to destination? Another aspect of performance is the bandwidth. How many packets can I send, or how much data can I send across the network over time? Cost primarily comes down to, because I'm running this on a chip, I'm taking up space that would go towards other logic. So the thought is, okay, if I have this very fancy router, then I'm taking away power, I'm taking away part of my space budget that could go to other logic. And so you have that balance of, okay, I want to optimize for performance, but I don't want it to cost me too much. And we'll see that throughout. Yeah. So you'll talk about like latency between two endpoints, and you could say, okay, depending on how your network, let's say I had a very specific application for this network, then I might care more about the performance between these two endpoints than these other two endpoints, and that's certainly something you would be concerned with if that's your design. Yes, in general, bandwidth isn't too big of a deal on an on-chip network, just because your data rate, like your links are actually pretty wide. Primarily, you're concerned with latency, and generally, the only time latency is going to be an issue is when you have you're oversubscribed, or you have more data coming on than you can handle, that you're getting towards your peak bandwidth. All right, so I'm going to briefly talk about routing. So here I've drawn just a two-dimensional mesh, and I'm going to talk about three different routing functions. The first, which is probably the simplest, is this dimension-ordered routing. What I'm going to do is, for a given packet, send it from the source to a destination. I send it as far along one dimension as it needs to go, and then once I reach that point along the dimension, so in this case I reach 2 on the x dimension, then I'll turn and I'll go along the y dimension to my destination. So in my router, I've implemented dimension-ordered routing. Just for completeness, I've listed a couple other routing algorithms. So oblivious routing is that at any point, I'll send it. So that's drawn this way. Both x and y are equally valid. At any point, I'm going to send it to any router that gets it closer to its destination. The reason it's called oblivious is because it's oblivious to network congestion. I don't know which one is better. I'll just send it to either of them with roughly equal probability, and that way I'm going to spread the load across the network, as long as I'm moving one hop closer to my destination. Obviously, with this network, from here I can go either way, and from here I can go either way, as long as I'm getting closer to the point. Adaptive routing does take into account what the network congestion is. So if I know at this point that this router is congested, I'll route here to avoid it and prevent that. Yep. Generally speaking, there's no such thing as link congestion. Any link, if I have to buffer at the router basically to allow myself to send downstream. Like if I have two people sending into this node, and that they both want to go that way, I would say they're congested at that router. The obvious point is that the bandwidth of these two is twice of this, which is typical. So the trade-off to be made here, you would say, okay, obviously adaptive routing is going to be best, but I want to point out that the trade-off is that these are more complicated, take up more space on the chip, more power. Dimension-ordered routing is pretty much the standard. You just use a simple routing mechanism to use it. And that's what I've implemented. I'll talk about flow control. So there's, I've given an example of 3 different flow control techniques. So again, the idea is that I have a packet and I separate it into pieces. And these are the pieces that I send from router to router. And probably the most simple flow control algorithm is store and forward, which is I've run these 4 different routers. And once I get the head flit, all the bodies, and the tail of my packet, once the tail has arrived, then I can send it downstream. So I store the entire packet at the router, and then once it's in its entirety arrived, I forward it downstream. And that proceeds so on and so forth. There are a couple issues with this. One is that I need to be able to buffer an entire packet. And 2, the latency. Every hop, the latency increases by the length of the packet. The sort of next step along that is what's called cut-through, which is that instead of storing the entire packet, I'll start sending the packet as long as I know that the downstream router could hold an entire packet. So in this case, channel 0 receives the head flit and knows that the next router can hold that packet. So it'll just start sending it next cycle, right? You get good latency in this case. Whereas router 1 may not send immediately to router 2 if there's not enough space for the whole packet. So I'm always going to send the whole packet contiguously. It's just that I can start sending it as soon as I've gotten the first bit of it downstream if I know that it can hold that. And then you have wormhole routing. And the idea here is that instead of sending an entire packet at a time and doing flow control based on packets, I'm going to do flow control purely based on flits. So here I show on my input, I receive the head and the body. And there's not enough room for me to send downstream immediately. So I don't have enough space for the whole packet, and that gets queued up behind. So all the other routers behind will have to queue up the rest of the packet. And as soon as I do have space to send downstream, I'll send them out and receive more pieces of the packet. And the value of wormhole routing is that I need much less space to buffer. I only really need enough space for 1 flit here, whereas I need more here. These both have the nice property that without congestion, you're getting 1 cycle per, or not necessarily 1 cycle, but you're not paying the cost of the length of the packet for every hop. So, yeah, go ahead. You're absolutely right. So typically you don't use the term flits for these two. I only do it because it comes into account there. So generally there's 2 terms. There's flit and then there's fit, P-H-I-T, which is a physical limitation. So I don't have width to send an entire packet. So I say whatever I can send, that's called a fit. The idea is that however I break this up, they all have to go to the same destination. And that's the purpose of talking about them as a packet, even though I can't necessarily send them all contiguously across the link or simultaneously across the link. So yeah, you normally don't talk about flits, or if you do, what you really mean is a fit, whatever the physical limitation is.